everyone, thanks for enduring a third part to this, and I didn't intend to cut it on the last one, but then I looked at things and was like, I probably should cut it because the case study's about the next 6 pages, and then there's like a real fast conclusion, and then we can look at the appendices. So, on to case study. Prompt engineering is emerging as an art that many people have begun to practice professionally, but the literature does not yet include detailed guidance on the process. As a first step in this direction, we present an annotated prompt engineering case study for a difficult real-world problem. This is not intended to be an empirical contribution in terms of actually solving the problem, and rather it provides one illustration of how an experienced prompt engineer would approach a task like this, along with lessons learned. So let's sit up and pay attention if we were napping in the last 80 minutes. This is how we apply all the things we learned. So, our illustrated problem involves detection of signal that is predictive of crisis-level suicide risk in a text written by a potentially suicidal individual. Suicide is a severe problem worldwide, compounded, as are most mental health issues, by a desperate lack of mental health resources. In the United States, more than half the national population lives in a federally defined mental health provider shortage areas. In addition, many mental health professionals lack core competencies in suicide prevention. In 2021, 12.3 million Americans thought seriously about suicide, with 1.7 million actually making attempts, resulting in over 48,000 deaths. In the U.S., suicide was the second leading cause of death after accidents in people aged 10 to 14, 15 to 24, or 25 to 34 as of 2021 statistics, and it was the fifth leading cause of death in people aged 35 to 54. Recent research suggests there is a significant value in assessments of potential suicidality that focus specifically on the identification of suicidal crisis, i.e. the state of acute distress associated with high risk of imminent suicidal behavior. However, validated assessments for diagnostic approaches such as suicide crisis syndrome and acute suicidal affective disturbance require either personal clinical interactions or completion of self-report questionnaires that contain dozens of questions. Yes, I hate doing those every time I go before my therapy. And occasionally, you put something in, the system gives you the angry red flag. You're like, yeah, well, I've been like that a while. The ability to accurately flag indicators of crisis in individuals' language could therefore have a large impact within the mental health ecosystem, not as a replacement for clinical judgment, but as a way to complement existing practices. As a starting point, we focus here on the most important predictive factor in suicide crisis syndrome assessments, referred to in the literature as either frantic hopelessness or entrapment, aka desire to escape from an unbearable situation tied with the perception that all escape routes are blocked. And I don't know if I would use the word entrapment for this, and I will try not to get my brain confused with the legal definition of entrapment, which I'm much more familiar with. This characteristic of what an individual is experiencing is also central in other characterizations of mental processes that result in suicide. So frantic hopelessness, that makes sense, or you can't get out of the situation, and so that's the last route. All right, so the data set. We work with a subset of data from the University of Maryland's Reddit suicidality dataset, which is constructed from posts in our Suicide Watch, a subreddit that offers peer support for anyone struggling with suicidal thoughts. Two coders trained on the recognition of the factors in suicide crisis syndrome coded a set of 221 posts for presence or absence of entrapment, achieving a solid intercoder reliability of 0.72. I miss doing social science coding. Anyway. Fun jobs I had in the past. The process. An expert prompt engineer who's authored a widely used guide on prompting took on the task of using an LLM to identify entrapment in posts. All right, we have some notes, so I'm definitely going to scroll down here. So the former term more explicitly emphasizes the frantic and desperate action required to escape an unbearable life, that hopelessness thing. However, the term entrapment is briefer and used widely, so we adopt it here. So the former term, I'm guessing, is... not entrapment, but frantic hopelessness. See, I would rather use frantic hopelessness, but you guys let me know if you have any sort of preference on that. Because again, entrapment, I mean, you are trapped, but I don't know. Again, I have legal issues. That's where my brain goes when I hear that. So disclosure, the expert is also the lead author of this paper. Okay, so conflict of interest possibly. The prompt engineer was given a brief verbal and written summary of suicide crisis syndrome and entrapment, along with 121 development posts and their positive negative labels, where positive means entrapment is present. The other 100 label posts being reserved for testing. The limited information mirrors frequent real-life scenarios in which prompts are developed based on task description and the data. More generally, is consistent with a tendency in natural language processing and AI more generally to approach coding annotation as a labeling task without delving very deeply into the fact that the labels may in fact refer to nuanced and complex underlying social science constructs. Yes, much like classifying things in library science. We documented the prompt engineering process in order to illustrate the way that an experienced prompt engineer goes about their work. The exercise proceeded through 47 recorded development steps. Cumulatively about 20 hours of work from a cold start with 0% performance. Prompt won't return any properly structured responses. Performance was boosted to an F1 of 0.53, where that F1 is the harmonic mean of 0.86 precision and 0.38 recall. And if you have no idea what that means, maybe this footnote will help us. So precision is known as positive predictive value, so the ability to get things right, and recall is also known as true positive rate or sensitivity. Although F1 is often used in computational system evaluations as a single figure of merit, we note that in this problem space, its even weighting of precision and recall is probably not appropriate. We discuss this further below. Not in other footnotes, sorry. Okay. So below the set of prompts, Q and F is the test item where Q, I, R, I, and A, I denote the question's chain of thought steps and answers in exemplar. So data set exploration 2 steps. Process began with the prompt engineer reviewing a description of entrapment. This description had been used as a first pass rubric for the human coders early in the coding process, noting, however, that they were familiar with suicidal syndrome and knew it was neither a formal definition nor exhaustive. The prompt engineer then loaded the data set into a Python notebook for data exploration purposes. He began by asking GPT Turbo Preview if it knew what entrapment was, but found the LLM's response was not similar to the description that had been given. In consequence, the prompt engineer included the figure 6.7 description of entrapment in all future prompts. So let's see, we have 7 and 8. Is that up here or down there? 6.3, so this is probably further down. Okay, so 6.5 F1 scores, varying widely from worst performing to highest performing, but most scored within a similar range. And I'm turning my head, and there's all these different types: zero shot context, triplicate context. Anyway, trying to find the other diagrams for us before we pause for the exciting pauses we have to take for my lovely furnace. So prompting techniques on a development set. Okay, interesting. Figure 6.6. From the first prompt tried zero shot context to the last anonymized email, improvements in F1 score were hard to come by and often involved testing multiple underperforming prompts before finding a performant one. Green lines show improvements over the current highest F1 score, while red lines show deteriorations. Oh, well, that's not encouraging. And then they also mentioned 6.7, which is where I wanted to get, the description of entrapment used by the prompt engineer. Feeling like there is no exit, feeling hopeless, feeling like there's no way out, feeling things will never be normal, feeling helpless to change, feeling trapped, feeling doomed, feeling or thinking things will never change, feeling like there is no escape, feeling there's no good solutions to problems. And then it asked it, was entrapment with respect to suicide crisis syndrome, and whether the training data provide any relevant knowledge. Apparently not. So we're 6.9 here. If you are in immediate danger of harming yourself, please contact emergency services or a crisis hotline in your area. They can provide immediate support and help ensure your safety. Snippet from an output which does not label the data point, but rather attempts to provide mental health support. Such outputs are often 5 times as long as this snippet. Oh, well, that's not great. Okay, I'm getting ahead of ourselves. All right. Just trying to figure out how far back I need to go. Sorry. Got a little lost here. Okay, so descriptive entrapment, all future prompts. Okay. Getting a label. 8 steps. As noted in section 6.1, with regard to the human sexuality subset of MMLU, large language models exhibit unpredictable and difficult to control behavior in sensitive domains. For multiple steps in the prompt engineering process, the prompt engineer found that the LLM was giving mental health advice instead of labeling the input. This was addressed by switching to the GPT-432K model. A takeaway from this initial phase is that the guardrails associated with some large language models may interfere with the ability to make progress on a prompting task, and this could influence the choice of model for reasons other than the LLM's potential quality. Prompting techniques, 32 steps. The prompt engineer spent the majority of his time improving the prompting technique being used. These included techniques such as a few shot, chain of thought, auto chain of thought, contrastive chain of thought, and multiple answer extraction techniques. We report statistics for the first runs of these techniques. F1 scores could change by as much as 0.04 upon subsequent runs, even with temperature and top P set to 0. Zero shot plus context. Oh, temperature and top P are configuration hyperparameters that control the randomness of the output. I'm just making sure precision, positive predictive value, and recall is positive, true positive rate of sensitivity. Often use computational. Probably not appropriate. Yep, okay. We already looked at that part. Okay, zero shot context was the first technique evaluated using the description figure 6.7. Notice the word definition in the prompt, although figure 6.7 is not a formal definition. In order to obtain a final response from the large language model to use in calculating performance metrics, it was necessary to extract a label from the large language model output. The prompt engineer tested two extractors, one that checks if the output is exactly yes or no, and another which just checks if those words match the first few characters of the output. The latter had better performance and is used for the rest of this section until we reach train of thought. This approach obtained 0.4 F1 1.0 recall and 0.25 precision evaluated on all samples from the training development since no samples had been used as exemplar. 10 shot plus context. Next, the prompt engineer added the first 10 data samples with labels into the prompt in QA format. He evaluated this 10 shot prompt on the remaining items in the training development set, yielding an increase of 0.05 F1 and a decrease of 0.09 in the recall and an increase of 0.05 in the precision relative to the previous best prompt. And seeing as we keep mentioning these lovely diagrams, let's look at figure 6.10 and 6.11 here. This is 6.6, where are we? 6.10. A zero shot plus context prompt, the simplest of all prompts is stored in the case study. Entrapment definition, is this entrapment? Yes or no? Figure 6.1, the 10 shot plus context prompt was the one we just looked at. So figure 6.7, question 1, answer 1, for eternity. All right. A one-shot auto-dicot plus full context, but first, this little footnote. Here and by for the remainder of the case study, we judge best by F1 and report on the current prompt under discussion relative to the best performing previous prompt. Okay. So, face off. One-shot, auto, dicot, and full context. After performing 10-shot prompting, the prompt engineer observed the 12th item in the development set was being incorrectly labeled as a positive instance and began experimenting with ways of modifying the prompting such that the model would get the item correct. In order to get a sense of why this mislabeling was taking place, the prompt engineer prompted the LLM to generate an explanation of why the 12th item would have been labeled the way it was. We're trying to avoid using misleading language, like the generated explanation of its reasoning. They do not have access to their own internal processes, and therefore they cannot explain their reasoning in the usual sense. A large language model generating an explanation is producing a description of potential reasoning steps and getting to the output that could be true, but also may not be accurate at all. Could just straight up be lying to you. Okay, that's not reassuring. Figure 6.9 we already looked at, so okay. 19, just checking. Figure 6.12 shows a version of that process generalized to produce explanations for all developmental question and answer items in a set T rather than just item 12. Informed by reasoning steps R12 elicited with respect to the incorrectly labeled Q12, the previous prompt was modified by including R12 in a one-shot chain of thought example with incorrect reasoning as an exemplar of what not to do, as shown in figure 6.13. So let's put 1.2 and 1.3. So 1.2, algorithm, automatic, directed, chain of thought, required development items T with n pairs for each pair in T. Label 1 is entrapment or not entrapment using the model. If the model labels correctly, prompt the model with Y to generate a reasoning chain R sub I. Else, prompt the model with it actually is not entrapment. Please explain Y to generate reasoning chain R sub I. Store the tuple. Questions I, R sub I, answer sub I, return n tuples, Q I, R I, A I. And then in figure 6.13, one-shot autodicot plus full context. Only label the post as entrapment. Oh, I'm sorry. Professor's email entrapment definition. Only label the post as entrapment if they explicitly say they feel trapped. Q12, our response, although today I found out I have 10 days to vacate my apartment or I'll be formally evicted. I'm 2 months behind on my rent due to a bad time where I got demoted at work and went from making roughly $1,000 over 2 weeks to around $450. If I get evicted, I'll probably be homeless. Seems to express feelings of being trapped / stuck, but is not sufficiently explicit to be labeled entrapment. Makes sense. Okay, back up. So we got to look at that. We call the algorithm in figure 6.12 automatic directed chain of thought, or IO-dicot, since it automatically directs the chain of thought processes to reason in a particular way. This technique can be generalized to any labeling task. Sit up, librarians. We label lots of things. It combines the automatic generation of chain of thoughts with showing the LLM examples of bad reasoning, as in the case of contrastive chain of thought. The algorithm was also used in developing later prompts. Finally, the prompt was extended with 2 additional pieces of context and instruction. The first was an email message the prompt engineer had received explaining overall goals of the project, which provided more context around the concept of entrapment and the reasons for wanting to label it. The second edition was inspired by the prompt engineer noticing the model is frequently over-generating a positive label for entrapment, hypothesizing that the model is being too aggressive in its pre-training-based inferences. From the overt language, he instructed the model to restrict itself to explicit statements of entrapment, which is the figure we just looked at. Makes sense, again. Below, we refer to these 2 pieces of context provided in addition to description of entrapment as full context. And I don't know if I necessarily like this whole mental classification by AI thing either. Yeah, humans make enough mistakes with that. A new extractor was also used for this prompt, which checks whether the last word in the output is yes or no instead of the first word. This updated prompt was tested against all inputs in the development set except for the first 20. It did not improve F1, decrease of 0.09, but it led the prompt engineer a direction that did, as discussed below. Recall dropped to 0.58, and recall and precision improved to 0.09 precision. At this point, though, it's worth observing that, although it did ultimately lead to a gain in F1 score, the steps taken here cut down on an overgeneration of positive labels were not, in fact, the right move in terms of the longer-term goals. Dang. Entrapment need not be expressed explicitly in order to be present, though phrases like I feel trapped or there's no way out. Rather, clinical experts who have looked at the text found the expressions of entrapment could be implicit and potentially quite nuanced, and that's where it gets weird. As someone who has, been investigated in her juvenile years for writing things long before there was an internet. Yeah. People's interpretations of unclear statements can often get you in trouble even if they're not AI. So just think about that. All right. Moreover, in most use cases for automatically spotting entrapment in someone's language, precision and recall are unlikely to be equally important. And of the 2, the recall, sensitivity, not missing people who should be flagged at risk may matter more because the potential cost of a false negative is so high. Yeah, you don't want someone to be missed. The takeaway here, although the insight came later, is that it's easy for the process, being relative, for the process of prompt development to diverge from the actual goals unless a regular engagement is fostered between the prompt engineer and the domain experts who more deeply understand the real-world use case. So check in with your clients. A blading email. The results of the previous changes were promising, but they did involve creating a prompt that included information from an email message that had not been created for that purpose and which included information about the project, dataset, etc. that were not intended for disclosure to a broad audience. Ironically, removing this email brought performance significantly down, 0.27 F1, 0.75 recall, and 0.1 precision. We attribute this to the fact that the email provided richer background information about the goals of the labeling. Although we would not recommend including email or any other potentially identifying information in any large language model prompt, we chose to leave the email in the prompt. This is consistent with scenarios in many typical settings in which prompts are not expected to be exposed to others. And also why our lovely IT department is like, no large language model AI for you guys. You should not be playing around with ChatGPT because there's way too much stuff that it may be able to extract and remember and share with other people. All right, 10 shot plus 1 auto die cut. As a next step, the prompt engineer tried using full context, 10 regular exemplars, and the 1-shot exemplar about how not to reason. This hurt performance, down 0.3 F1, 0.08 recall, 0.03 precision. Full context only. Next, the prompt was created using only full context without any exemplars. This boosted performance over the previous technique, but did not make progress overall. Down 0.01 F1, up 0.01 recall, down 0.01 precision. Interestingly, in this prompt, the prompt engineer accidentally pasted in the full context email twice, and that ended up having significant positive effects on performance later, and removing the duplicate actually decreased performance. So this is reminiscent of the rereading technique. Huh, that's an interesting thought there. All right, and what diagram do I need to go look at? 6.15. Oh, that's 1615. Must be up here. Entrapment definition. Okay, so this is the professor email twice. This can be interpreted both optimistically and pessimistically. Optimistically, it demonstrates how improvements can rise through exploration and fortuitous discovery. On the pessimistic side, the value of duplicating the email in the prompt highlights the extent to which prompting remains a difficult-to-explain black art, where the large language model may turn out to be unexpectedly sensitive to variations one might not expect to matter. Oh, been there, done that. 10 shot, auto die cut. The next step was to create more auto die cut exemplars per the algorithm in figure 612. A total of 10 new auto die cut exemplars were added to the full context prompt in figure 6116. This yielded the most successful prompt from this prompt engineering exercise in terms of F1 score, up 0.08, and down 0.05 recall, and up 0.08 precision. So I'm going to look at 612. Nope, we've already passed that. 616, where is 616? 616, 10 shot auto die cut. Entrapment definition, only label the post if they explicitly say they are entrapped. Yeah, that's right. Excuse me. 20 shot auto die cut. Further experimentation proceeded, seeking unsuccessfully to improve on the previous F1 result. In one attempt, the prompt engineer labeled an additional 10 exemplars and created a 20 shot prompt from the first 20 data points in the development set. This led to worse results than the 10 shot prompt when tested on all samples other than the first 20. Down 0.04 F1, up 0.08 recall, down 0.05 precision. Notably, it also yielded worse performance on the test set. So more is not necessarily better. Signal versus noise ratio, kids. 20 shot auto die cut and full words. The prompt engineer conjectured that the large language model would perform better if the prompt included full words, question, reasoning, and answer, rather than Q, R, and A. However, this did not succeed, as in figure 6.17. Down 0.05 F1, up 0.08 recall, down 0.06 in precision. So this is the 20 shot auto die cut. Only label is explicitly disabled, so question, answer, question, yeah, figure 1.7. Okay. 20 shot, auto die cut, full words plus extraction prompt. The prompt engineer then noticed that in many cases the large language model generated outputs that could not properly be parsed to obtain a response. So they crafted a prompt that extracted answers from the large language model's response. Although this improved accuracy by a few points, it decreased F1 thanks to the fact that many of the outputs that had been unparsed actually contained incorrect responses, down 0.05 F1, down 0.05 precision with no change in recall. So that yields 6.18, the extraction prompt, redacted, answer. Does the answer indicate entrapment? Output yes if labeled entrapment, no if it is not, only output yes or no. The 10-shot auto die cut plus extraction prompt. Applying the extraction prompt to the best performing 10-shot auto die cut prompt did not improve results. Down 0.04 F1, down 0.08 recall, down 0.03 precision. The 10-shot auto die cut without email. As noted above, removing the email outright from the prompt hurt performance because that had all the context in it. Down 0.14 F1, down 0.39 recall, down 0.06 precision. Deduplicating the email, as noted above, it seemed reasonable that removing the duplication of the email would perform as well or better than the prompt with the unintentional duplication, but as it turned out, removing the duplicate significantly hurt performance. Down 0.07 F1, down 0.12 recall, down 0.05 precision. Yeah, that's interesting. I'm just leaving it there. The 10-shot auto die cut was default to reject. This approach used the best performing prompt and defaulted to labeling as negative, not entrapment, in the case of answers that are not extracted properly. This did not help performance, down 0.11 F1, down 0.04 recall, down 0.10 precision. Ensemble plus extraction, especially for systems that are sensitive to the details of their inputs. There are advantages in trying multiple variations of an input, then combining the results. That was done here by taking the best performing prompt, the 10-shot auto-die-cut prompt, and creating 3 versions of it with different orderings of the exemplars. The average of the 3 results was taken to be the final answer. Unfortunately, both orderings that differed from the default ordering led to the LLM not outputting a well-structured response. An extraction prompt was therefore used to obtain final answers. This exploration hurt rather than helped performance, and down 0.16 F1, down 0.23 recall, down 0.13 precision. 10-shot auto-cut plus 3 times the context, no email duplication. Recall that context refers to the description of entrapment and instruction about explicitness in an email. Since the duplicated email improved performance, the prompt engineer tested out pasting in 3 copies of the context, first deduplicating the email. However, this did not improve performance. Down 0.06 F1, down 0.08 recall, down 0.05 precision. Anonymizing the email. At this point, it seemed clear that including the duplicated email in the prompt was actually, although not explainably, essential to the best performance so far obtained. We don't know why, but it works. This sounds like 95% of my job right there. It works. Why are we questioning it? Just make the robot happy. The prompt engineer decided to anonymize the email by replacing personal names with other random names. However, that surprisingly decreased performance significantly. Down 0.08 F1, down 0.14 recall, down 0.06 precision. So, yeah, it needs to know all your business, apparently. DSPy, we concluded the case study by exploring an alternative to manual prompt engineering, the DSPy framework, which automatically optimizes LLM prompts for a given target metric. Specifically, we begin with chain of thought classification pipeline that uses the definition of entrapment in figure 6.7. Over 16 iterations, DSPy bootstrapped synthetic LLM generated demonstrations and randomly sampled training exemplars, with the ultimate objective of maximizing F1 on the same development set used above. We used GPT-40125 preview and the default settings for the bootstrap fuse shot with random search teleprompter optimization approach. Figure 6.19 shows the results of 2 of these prompts in the test set, one of which used default DSPy behavior, and the second of which was manually modified slightly from the default. The best resulting prompt includes 15 exemplars without chain of thought reasoning and 1 bootstrapped reasoning demonstration. It achieves a 0.548 F1, 0.385, and 0.952 precision recall on the test set. Without making any use of the professor's email, nor the incorrect instruction about the explicitness of entrapment, it also performs much better than the human prompt engineer's prompts on the test set, which demonstrates the significant promise of automated prompt engineering, which was covered in the article we did just before this one a few days ago, and is not nearly as long, so don't worry. If you got another 45 minutes to spare, feel free to keep on going on this playlist. So yeah, scores of different prompting techniques on the test set. So, yeah, okay. The machines can talk to each other better than we can. Well, that's not terribly surprising. Discussion. Prompt engineering is a non-trivial process, the nuances of which are not currently well described in the literature. From the fully manual process illustrated above, there are several takeaways worth summarizing. First, prompt engineering is fundamentally different from other ways of getting a computer to behave the way you want it to. These systems are being cajoled and not programmed, and in addition to being quite sensitive to the specific large language model being used, they can be incredibly sensitive to specific details in prompts without there being any obvious reason those details should matter. So if you really want to have a fun career talking to the bots, get into prompt engineering. Second, therefore, it is important to dig into the data, e.g. generating potential explanations for large language model quote-unquote reasoning that leads to incorrect responses. That's why I like the transparent AI idea. Related, the third and most important takeaway is that prompt engineering should involve engagement between the prompt engineer who has expertise in how to coax the LLM to behave in desired ways, and domain experts who understand what those desired ways are and why. Yeah, or anyway, don't get me started on software engineers that don't seem to understand what they're engineering. I won't name our vendor. Anyway, ultimately, we found there was a significant promise in automated method for exploring the prompting space, but also that combining that automation with human prompt engineering and revision was the most successful approach. Yes, co-learning, interactionality, good stuff. We hope that this study will serve a step toward more robust examinations on how to perform prompt engineering. Now we're just going to go into this lovely related work. So in this section, we review existing surveys and meta-analyses of prompting. Liu et al. Perform a systematic review of prompt engineering in the pre-ChatGPT era, including various aspects of prompting like prompt template engineering, answer engineering, prompt ensembling, and prompt tuning methods. Their review covers many different types of prompting, e.g. closed, soft prompting across many different types of language models, while we focus on discrete prefix prompting but more in-depth discussion. Chen et al. Provide a review of popular prompting techniques like train of thought, tree of thought, self-consistency, and least to most prompting, along with outlooks for future prompting research. White et al. And Schmidt et al. Provide a taxonomy of prompt patterns, which are similar to software patterns and prompting techniques for that matter. Zhao provide a practical prompting technique tutorial for a non-technical audience. Probably should go check that out. Sentu and Feng provide a general taxonomy of prompts that can be used to design prompts with specific properties to provide a wide range of complex tasks. Bubeck et al. Qualitatively experiment with a wide range of prompting methods on the early version of GPT-4 to understand its capabilities. Chu et al. Review chain of thought related prompting methods for reasoning. In earlier work, Bommasani et al. Review and discuss opportunities and risks of foundation models broadly, and Dang et al. Discuss prompting strategies for interactive creative applications that use prompting as a new paradigm for human interaction, with a particular focus on the user interface design that supports user prompting. As an addition to these existing surveys, our review aims to provide a more updated and formalized systematic review. All right. There is also a line of work that surveys prompting techniques for particular domains or downstream applications. Mesko and Wang et al. Offer recommended use cases and limitations of prompt engineering in the medical and healthcare domains. Heston and Kuhn provide a review of prompt engineering for medical education use cases. Peskov and Stewart query ChatGPT and UChat to assess a domain coverage. Hua et al. Use a GPT-4 automated approach to review large language models in the mental health space. Wang et al. Review prompt engineering and relevant models in the visual modality, and Yang et al. Provided a comprehensive list of qualitative analyses of multimodal prompting, particularly focusing on GPT-4v. Durante et al. Review multimodal interactions based on large language model embodied agents. Ko et al. Review literature on the adoption of text-image generation models for visual artist creative works. Gupta et al. Review GenAI through a topic modeling approach. Awais et al. Review foundation models in vision, including various prompting techniques. Hu et al. Perform a systematic review of prompt engineering techniques as they relate to software engineering. They use a systematic review technique developed by Keel et al. Specifically for software engineering reviews. Wang et al. Review the literature on software testing with large language models. Zhang et al. Review a ChatGPT prompting performance on software engineering tasks such as automated program repair. Niagu provide a systematic review on how prompt engineering can be leveraged in computer science education. Li et al. Review literature on the fairness of large language models. There are also surveys on related aspects such as hallucination of language models, verifiability, reasoning, augmentation, and linguistic properties of prompts. Different from these works, we perform our review targeting broad coverage and generally applicable prompting techniques. Finally, in terms of a more general pride and concurrent surveys, this survey offers an update in a fast-moving field. In addition, we provide a starting point for taxonomic organization of prompting techniques and standardization of terminology. Moreover, unlike many works that claim to be systematic, we base our work on the widely used standard for systematic literature reviews, Prisma. So, some conclusions. Generative AI is a novel technology, and broader understanding of models' capabilities and limitations remains limited. Natural language is a flexible, open-ended interface with models having few obvious affordances. The use of generative AI therefore inherits many of the standard challenges of linguistic communication, e.g. ambiguity, the role of context, the need for course correction, while at the same time adding the challenge of communicating with an entity whose understanding of language may not bear any substantial relationship to human understanding. Because keep in mind, when it's parroting off sentences, it's just using that based off a probability and what word it thinks comes next. You know, it's literally like a parrot. It doesn't understand what it's saying. Many of the techniques described here have been called emergent, but it's perhaps more appropriate to say that they were discovered, the result of thorough experimentation, analogies from human reasoning, or pure serendipity. The present work is an initial attempt to categorize the species of an unfamiliar territory. While we make every attempt to be comprehensive, there are sure to be gaps and redundancies. Our intention is to provide taxonomy and terminology that cover a large number of existing prompt engineering techniques and which can accommodate future methods. We discuss over 200 prompting techniques, frameworks built around them, and issues like safety and security that need to be kept in mind while using them. We also present 2 case studies in order to provide a clear sense of models' capabilities and what it is like to tackle a problem in practice. Last, our stance is primarily observational. We make no claims to the validity of the presented techniques. The field is new and evaluation is variable and unstandardized. Even the most meticulous experimentation may suffer from unanticipated shortcomings, and model outputs themselves are sensitive to meaning-preserving changes in inputs. As a result, we encourage the reader to avoid taking any claims at face value and to recognize that techniques may not transfer to other problems, models, or datasets. To those just beginning in prompt engineering, our recommendations resemble what one would recommend in any machine learning setting. Understand the problem you are trying to solve rather than just focusing on input, output, and benchmark scores. And ensure the data and metrics you are working with constitute a good representation of the problem. It is better to start with simpler approaches first and remain skeptical of claims about method performance. To those already engaged in prompt engineering, we hope our taxonomy will shed light on relationships between existing techniques. To those developing new techniques, we encourage situating new methods within our taxonomy, as well as including ecologically valid case studies and illustrations of those techniques. And we appreciate the advice be given by Hal Duame III, Adam Vioske, and Jordan Boyd Graber, and the review by D. Yang, Brandon M. Stewart, Subhan Vatsal, Mason Marchetti, Aaron Tay, Andrea Vella, and Allie Miller. We also appreciate the 10K United States dollars in API credits given by OpenAI and design work by Benjamin DeMarco. And we are going to get into the references and things, which is why I kept this sidebar over here ready to go. Just so we could click around a little bit and see what the options are. Okay, I think I got that to collapse. So definitions of prompting, references, oh, exciting stuff. We have an extended vocabulary of prompting terms. So if you, like me, are less than familiar with some of this, orthogonal prompt types, that was one where I was kind of like, what does that mean? So yeah, originator, system prompts, hard versus soft. They touched on that a little bit. There is also a data sheet down here. So we present a data sheet with more information about associated paper data set, host on Hugging Face. So yeah, we talk about motivation, composition, and collection process, pre-processing, cleaning, labeling, uses, distribution, and maintenance. And then there's a bunch of keywords. Prompt for systematic literature review. So if you want to figure out exactly how they ask them to find the examples for the literature review. We have an evaluation table. Ooh, funsies. So E explicit, whether it generates an assessment. I implicit, whether it's derived from the model output. I response is single, multiple, model generated instruction. Lots and lots of detail. If you are into that sort of thing, we have the entrapment prompting process. So containing the thought process of the prompt engineer as he developed the prompt. So this actually sounds like it could be somewhat useful. I'll go through this a little bit. So exploration, look at length, the label distribution, checked if GPT 11.6 preview understood entrapment, it did not. Getting a label, showing the definition, the response saying I should seek mental health support, which probably cracked you up. Got a similar response, appending in this entrapment, got to actually respond with the label. I gave it a reject example, but accepted as accept. Sometimes it gives emotional responses about getting help. Using 10 shots, still get the help responses. Tried removing the definition, got the same problem. It seems it doesn't like accept reject as labels. Added back the definition. Changing labels to entrapment, not entrapment. Often says not enough info. And I switched to GPT 432K, which gave one-word responses. Quickly projected a reject and accept data point. So then we varied the prompting techniques, tested 0-shot, 10-shot, first failing instance into playground, tried doing a let's go step by step, let's go step by step. Before predicting a label, let's go step by step, outright the thought process. Before, again, discussing the AI, don't they ever feel trapped? Output. Asked it to reformulate instructions, make explicit listen where clearly needed, still predicts entrapment, add entrapment must be explicit, not implicit. At the top, after the definitions, also tried with the previous chain of thought inducers, still says entrapment, a hard to parse out way. And if the person does not explicitly, still entrapment. Talking to AI, thanks today, I found 10 days vacant in my apartment, I'd be homeless, is feeling trapped, stuck. Try before staying unravel, write out the reasoning while it still thinks it's entrapment. Above definition, remove the shots, edit the shots. Yeah, this is exciting stuff. I know this is sort of exciting notes I write, but you know. Oh, well, important. Only label is if they explicitly say it's entrapment. Try for the next wrongly label one. Test this on everything. So the first 20 did pretty well. I tried moving the email and the performance dropped off a cliff. And at this point, I'm thinking that giving examples with reasoning helps, obviously. Tried to add in 10 shots for free, but the last one with the reasoning gave us bad results. So, auto chain of thought. Develop the data set using the prompt and then ask it why. If it disagrees, I say, is it actually not? Please explain why. Just for fun, tried zero shot. Had to adjust the verbalizer. Tried this with a special verbalizer. Adjust my generate data, beat the 0.5 F1, doing 10 more exemplars with auto chain of thought, and sometimes responds immediately with reasoning like this post does not meet the criteria, so just use that. So sometimes I get the refusal of like, I'm really sorry to hear it this way. Just explain why it is not entrapment. Performance didn't really improve. My desire inability to parse, about 16%. Did worse, iterating on email, tried best preference, tried without the email, tried moving things around, just tried things. So as you can see, there's a lot of just trying things. So formally defining a prompt, so as a conditioning mechanism, woohoo, formulas. Yeah, templating, more formulas, more exciting math. Those of you that don't remember that computer science is based out of mathematics, here's exciting stuff. All right, I'm going to move on from this. Formally defining a prompt. Oh, I think, okay, I bumped into the next section. My bad. In context learning, definitions and disambiguation. Some natural language instruction, a few demonstrations, few shot learning. We allow as many demonstrations to fit into the model's context window. Includes this image that clarifies the matter. 3 settings we explore for in-context learning. 0 shot predicts the answer given only natural language description. 1 shot, the model sees a single example. No gradient updates are performed. Traditional fine-tuning, repeated gradient updates using a large corpus of example tasks. Few shot, in addition to task description, it sees a few examples. No gradient updates performed. And additionally, they explicitly state that ICL does not necessarily involve learning anything new. So to avoid the term, we use the term meta-learning. The terms are intended to make agnostic the question whether the model learns new tasks from scratch at inference or simply recognizes patterns seen during training. We, don't think too deeply about that, and then we get to all of our friends, the contributors. Okay, if you have stayed with me through this whole super long series of videos on the prompt report, a systematic survey of prompting critiques from Schulhof et al. Congratulations, this has taken up probably far too long of my business day, but I learned a lot. I don't know how to apply all of it, but I definitely learned a lot, and that's a pretty dang good reference if you want to start getting into this sort of thing.